So welcome to the afternoon session. So our first speaker of the afternoon session is Alok Laddha from Chennai, who will tell us about Introduction to Positive Geometries. So over to you. Thank you.
Okay, can you hear me? Okay, so thanks, Suvrat. So I'm supposed to give 2 lectures, and my lectures are going to be some introductory explanation of what these objects are, which are called positive geometries. So these lectures will not require you to know what positive geometries are. And I should also apologize to experts because they will be very elementary, but hopefully towards the end of the second lecture, I will be able to tell some interesting things that we have been able to do with these recently. And please stop me at any time, because some of the things today we will do will be a bit more mathematical. So if there is something which is not clear, then please ask me. So let me give you, already Johannes gave us a more motivation for why we look at some of these geometries. But let me give you some slightly different motivation also, which is that, so, there are many, now we know many methods that Johannes touched on to compute S matrix in, for example, in supersymmetric theories as well as in ordinary quantum field theories. And these methods, let me categorize some of them. So the first method is that we know in textbook QFT method, which goes under the name of Feynman diagrams. So of course, throughout the lectures, I will only talk about perturbative expansion of the S matrices, and will not have anything to say about non-perturbative structure of these amplitudes. So of course, when we have perturbation theory is valid, then we can do expansions in Feynman diagrams and do our usual S matrix computations. But in last 20-30 years, there have been many other methods. For example, there is, which I think Shruti will talk about, what are known as on-shell recursions. Which compute tree-level amplitudes, or as Johannes explained, loop-level integrands from lower point amplitudes. And one of the interesting thing about, there's already a conceptual difference between these two, in the sense that here we preserve unitarity and locality at every step of our computation, because that's how Feynman diagrams are devised from Lagrangian descriptions, which are local, and unitarity is guaranteed by our I-epsilon prescription of the Feynman propagators. But in the on-shell recursion, what happens is that when you do the computation, as you will see in Shruti's lectures, locality is not preserved manifestly at intermediate steps of the computation. So unitarity is okay, and locality only emerges in the final result. So what seems like an indispensable postulates that we have to start with to compute S matrix, you already see that perhaps they are not perhaps the most fundamental ones, because you still get the correct answer even though you don't manifestly preserve locality. The another one, there are many other methods. Different method than on-shell recursion is what is known as worldsheet formulation. So again, if you have not seen this, it's absolutely okay. We will not use it. This is just to put the stuff we will talk about in some context. So in this worldsheet formulation, basically the structures are even more different than on-shell recursion, because you compute some, you do some integrals on some moduli spaces, and so at the beginning there is neither unitarity or locality which is manifest. And of course, in the end, it computes tree-level amplitudes or integrands, and so both of these structures kind of emerge. So, and we could go on. There are several other methods that I will not discuss. But this already tells us that perhaps the fact that there are these different avatars of S matrix via Feynman diagrams, recursion, or completely different structures on moduli spaces tells us that maybe there is some unified description which underlies any rational functions that we compute at tree level or at the level of integrand. So the basic question that arises from here is that is there a deeper structure that generates rational functions, for example, which precisely have singularities of the amplitude, which corresponds to singularities of the which are tree-level S amplitudes or integrands. So this is I want you to keep this question in mind, which this is one of the main motivations right now behind the stuff that we will discuss, tree-level amplitudes or integrands. And in the sense that the deeper structure should be such that it shouldn't really assume anything about unitarity or locality or any Lagrangian description. So just some quantity, geometric quantity we can compute, like as Johannes explained, volume, for example, such that those volumes are precisely amplitudes for some quantum field theory. So that's the basic question we want to understand. And so that's the basic goal. And so we don't want to assume any structure except what the kinematic data is. So the only structure we start with is that we are looking at theories in Minkowski space-time. So the only physics input we are going to start with to begin with is the kinematic structure, which is space of all Lorentz invariant external Lorentz scalars that you can construct out of external data. So if you have some momenta, some polarization, then the only structure that we are given are all possible. So that by kinematic structure we simply mean set of all pi dot pj, for example, epsilon I dot pj and epsilon I dot epsilon j. So this is the sort of the bare bone structure that we are given, nothing more. And then we want to understand, is there some deeper structure that we can use which doesn't refer to any physics and generates specifically functions which always qualify as S matrices of one or the other quantum field theory. So is the question okay? Maybe I can stop here and ask. Okay. So just for this lecture, we will, so in the second lecture, we will look at Yang-Mills theory also, but just for this lecture, just for today, we will only look at scalar field theories. Scalar field, I mean scalar field kinematic structures. So that just means we just have Mandelstam invariants. So that is just set of all Mandelstams for it. And of course, these are external momenta, so we know that they are on shell. So all of them satisfy a mass shell condition. We don't assume anything about masses. They can be different masses also. They can also be massless. So let me first tell you what this kinematic structure is, because that we will keep in mind when we, so what we are going to do is see that there are some very nice geometrical structures that arises in combinatorial theories, and we will use that to draw some pictures into the space of Mandelstam invariant. So let me first lay down what this kinematic space is. So this kinematic space has a convenient basis that we are going to keep in mind. So this is the kinematic space, by the way. And the kinematic space, but of course we know that all Mandelstam are not invariant. I mean, you will be familiar that for 4 particles, if you have a single mass m, then we know that s plus t plus u is m square. And just to set the notation, yeah. Yeah, you could. I just wrote some, absolutely. I just wrote some, that's why I put dots here. I just said whatever external, we are given some external quantum numbers and external data. Sorry, yeah. And in general, I just wrote here that only we have polarization. You could have extra data and you could have extra invariance. I'm just right now just restricting. In fact, today I'm only restricting that we have nothing except the momenta also. So one convenient basis for kinematic space, it's a simple thing to check that if you look at all independent, so of course, sorry, I should have said this, we know that these momenta satisfy because we are in Minkowski space, so these satisfy conservation equation. So total momentum is conserved and every momentum is on shell. And so you can do simple analysis to check how many of these are invariant. And it turns out that the dimension of the kinematic space for n particles. So we will refer to this kinematic space as script kn. And its dimension you can immediately check. It's n into n minus 3 by 2, assuming that the dimension of space-time is larger than the number of particles. So there is a, if the number of particles exceed the dimension, then of course you have more complicated constraints coming from the fact that these momenta are not linearly independent. But how we do in usual QFT, those constraints we put at the end of our computation. So to begin with, we start with this bare, nice space where we always assume we are in, if you want, infinite dimensions, for example. So there is no other constraint on your Mandelstam's except these two things. And then there is a, with this, there is a nice basis for Kn. No, yeah, it will be dimension dependent, of course. And right now I have not referred to any dimension. Yeah. Exactly. Yeah. So if a fixed dimension, you can have more. In any case, I put dots here because I was agnostic about all the possible kinematic structures you can construct. Yeah. Yeah, we don't have any control because we are fixing infinite dimension anyway, so we don't have anything. Gram constraints, exactly. Yeah, exactly. But those are always there. So what we do in QFT also, I mean, of course, I think maybe Johannes can say more, but of course we know that you could look at the basis of kinematic space, even assuming gram conditions for 6 particles and higher. These are called momentum twistors. But right now we will just look at the bare bone structure where we don't want to go to. We are working with Mandelstam's. So, there's a nice basis, and this basis is precisely of the following type. So it's we will always denote it as xij, and it's simply written as you choose any order. So let me write it, and then it will become clear. For I less than j. So you fix an order where I is necessarily less than j, and write down all such invariants, and you can check that there are this many in number, and so they form a nice basis for us. So just as an illustration, if you are in, can I write here, Suvrat, or should I go? It's fine, right? Yeah. So if we are in, again, if we are in 4 dimensions. Oh, okay, sorry. I less than j, which is less than or equal to n, of course. And so just to go in 4 dimension again, just to tie up with what we wrote earlier, for 4 dimension, you see that there should be 2 independent Mandelstam's, and this gives us a nice basis, which we wrote it like this. And just if you follow the definition, x13 is simply p1 plus p2 square, which is just s, and x24 is p2 plus p3 square, which is t. So of course you could have chosen, this is not a unique basis, you could have chosen a basis which is SNU, but this basis has an advantage that you fix an ordering of 1 to n, and it respects the ordering nicely. And it will be like key for us to discover these geometric structures to use this basis right now. Of course, you will see that there is a lot more structure will be obtained once we do diffeomorphisms on this kinematic space, like once we start rotating the basis in different ways. But for now, we fix this basis. Let me just say that if you are at one loop, so just to set up the notation again, so these are only, of course, these are the Mandelstam for any amplitude respect to what order you are in perturbation theory. But since we are talking about loop integrands, you immediately realize that you have more Mandelstam invariants because you are not integrated over the loop. So at the level of one loop integrand, you could convince yourself that, of course, you could see that, what are the all variables of the form. If L is a loop momentum, then L square, then pi dot L or some pi plus dot 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 pj dot l. These are all Mandelstam invariants. And so again, we have to find an independent basis here. And a nice basis in this space is the following. So we denote it as xi0, and that is summation I equal to, j equal to 1 to I minus 1 pj plus l the whole square. And you notice that this is telling us that if you are at I equal to 1, then you get simply L square. So it includes the L propagator in it. And so the kinematic space at one loop is a kinematic space that we wrote down before for tree level, and plus is generated by these variables which we call xi0 for all I less than n. And just a small caveat that in fact if you remember that in general when you do one loop computation, you would get diagrams like this. So this is, I'm just saying from what we know. I mean, it's not some data that we are going to use, but we know that we always get tadpole diagrams like this if you have a cubic vertex, for example. And this is a strange propagator, but okay, as a fake propagator, if I can write it as I can write the momenta coming in here is p1 plus dot 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 p4 square. Of course, I have to regularize it carefully, etc. But formally, when we have tadpoles, we get invariants like this, and these invariants have so far not been included because in Kn, remember that we didn't include, for example, in n equal to 4, we didn't include p1 plus p2 plus p3 plus p4 square because that's just 0. And so if at loop level, we have to include formally extra bases which are kind of abstract variables, which I will just write down here. It will become clear what happens to them when we go to the geometries. But right now I just wanted to keep this in mind. And we will denote them as xii, and they are really written as you go from pi all the way to pn, then you go to p1 all the way to pi minus 1 square. Okay, they are obviously 0 by momentum conservation, and they look completely crazy, but right now think of it as just as a notation. And we will see, maybe not today, but in the next lecture, how to really do these things carefully. But in any case, so that's the kinematic space for one loop, and we could generalize this also to higher loops. Exactly, yeah. So right now I'm just saying that at the level of geometry, at the level of kinematic data, if I'm just labeling all possible Mandelstam's which occur in all propagators, then I may be tempted to put this as an extra data which was not there in the tree kinematic space. Think of it as a formal label right now, because it will become important when we draw the geometry. Right now it is an abstract space labeled by some xij's, xi0 and xii. Okay. Yeah, so is there any question about this so far? So this is our basic kinematics. Yeah. No, doesn't assume planarity. The choice of basis absolutely is exactly. I mean, so as you have seen, like it is really, we have chosen a basis which respects planarity, but this is a kinematic space for the amplitude, like because it's like u is s minus 4m square minus s minus t. So okay, so now this is where physics ends for this lecture, and then we will go to some completely independent developments in a subject called Quiver representation theory that we will not assume. I will explain whatever is needed, but if you have any questions about this setup. So the goal is we will see that math gives us some natural geometries in this space and how those geometries give us amplitudes of large class of scalar quantum field theories. So that's the arena in which we will draw pictures basically, but the pictures will come from some other developments in representation theory. So okay, so if this is, yeah, absolutely, but the amplitude would be some differential form that will be defined on these spaces, and that differential form will be something that comes out of some completely independent analysis that we will start doing today. Okay, so the goal is that this is some very boring space. It's some Cartesian space with these abstract labels, And we will see that what kind of interesting geometric structures we can put on them, which naturally some other math developments give us. So, okay. So then, so now we don't have much to go by, but luckily mathematicians already have explored structures which kind of correlate with at least the labeling of this kinematic space. So the only thing that we should keep in mind is that, so let's first focus on the Kn only, just the kinematic space for tree level amplitudes. And that is labeled by xij, where I is less than j. So now what can we do with this? I mean, this is some abstract thing with this label, but we are going to start with something which, so you don't kill me, we are going to start with something which is going to look completely useless, but we will see how it will, it will be like a star of the show, and this star is called okay, so just to keep in mind the picture, n equal to 4, just remember that we have two bases. And don't worry about what these x's are, just look at this 1, 3 and 2, 4, that's it, only these labels. And now if you are, so okay, so we have two data, one is this 4, which is some index, and this labeling, which is this 1, 3 and 2, 4. And so there is a nice quiver that you can generate, which kind of identifies 4 external points, and it isolates in some precise way these indices 1, 3 and 2, 4. So let me draw and it will become clear what I'm saying. So let's just draw 4 dots like this. I'm going to call this 1. These are nothing to do with moment or anything. So now till I explicitly say we are not connected with any physics. It is something completely divorced from our kinematic space. I just so x14 is 0 by moment of conservation because x14 is p1 plus p2 plus p3 square. So it's m square. I mean, it's m square. It's not. It's for massless it's 0. Otherwise, it's some m square by momentum. So remember, we have pi square equal to mi square and summation pi equal to 0. Xij is pi plus dot 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 all the way pj minus 1 square. Okay, and now let's do the following thing. So let me just draw this. Let me tell you what this quiver is. So the quiver is very simple to draw. Draw 4 dots like this, which I'm distinguishing as some empty dots. Draw like a thick dot in the middle, and now draw following arrows. And the way you draw the arrow is the following. This is just some game we are playing. Put a clock here and a clock here. And then you draw the arrows such that you are clockwise in this region and this region. So there is a choice here. I could have put also clock here and here, here and here, but let's pick one choice for now. So if you put a clock here, then you see that clockwise means you go like this on these 2 arrows, and on these 2 you go like this. Okay, but now you see what happens is that this black dot is such that the arrows which are going towards 1 and 3 are outgoing. So this is what is called a peak, in the sense that this is a dot where you shoot outwards, you get 1 here and you get 3 here. But that doesn't happen with the other guy. The other one is where they are incoming. So that's so this is what we call a peak, and this is what we call a dip. And this is 4, and this is 2. So because there is a peak here and nothing else, because the peak is a unique, so there is a unique path which gives a peak. So we're going to label it as 1, 3 with a black dot. Okay, black dot is just to distinguish that it's not these hollow labels. But so we have already sort of in a weird way generated like one of these labels, which is a unique path which has a peak here. Is this clear? So I will do one more example, then it will be more. Peak is something that, so you take a vertex and both the arrows are outgoing. Okay, so that's why it's a peak. And here both the arrows are incoming, so it's a dip. Okay, but I'm labeling it with a notation which is the peak and not a dip. I'll come to that. Yeah, I'll come to that. Yes. So it's completely, you just have to choose a convention and stick to it. So you could have, if you had chosen this clock to be here, you will get opposite. No, you have to choose a, so you have to choose, so this is a quiver I'm generating. So this is a rule I'm giving that, but so, okay, so what I mean is the following, maybe this will answer your question. So I'm saying that I could have also done the following, where I could have put the clocks here and here. Okay, then what I will get is, you can check, then you will get this, and then I will call this 2, 4 dot. So if you had put the clocks in these two planes, and then you look at the orientation, you will get 1, 3 incoming and 2, 4 outgoing, and because then it's a peak at 2, 4. So I would have called it 2, 4 dot. So the labeling depends on where I'm putting the clocks. Okay, so you could also generate 2, 4 from this analysis by putting clocks in different planes. So right now the only thing I'm saying is that there is a nice quiver which generates the only data which doesn't refer to physics, which is this number, cardinality, and these abstract labels. Okay. Yeah, I'll come to your question. So, yeah.
What is the rule for like how many elements clock I can? Like, I mean, I could have, if I put 4 clocks.
Yeah.
There may be like.
Yeah, you cannot. You can put either these two or these two. So that's the rule.
I mean, in general, there is a rule.
There is a rule for each such. If I draw one more diagram, it will become clear what the rule is. But it's just a rule that for each. Maybe I don't, because rather than giving a math definition, let me just show the picture for the next. But let me tell one thing I think you are asking, which is that why am I not considering a leg which is say 2, 1? So notice 2, 1 has neither a peak or a dip here. So that path is not, so this quiver generates 2 paths, 1, 3 and 2, 4. 1, 3 is a path, so 1, 3 is this path, okay, this path, which has a peak at this black dot, and 2, 4 is this path, which has a dip at this black dot. Okay, the dot is always 1, 3 dot. So the reason I'm distinguishing, so now you can say why is it not generating 2, 1 path? The reason is 2, 1 has no peak or dip here. So any path which has not a single peak or dip, we ignore it. Okay, so I hope, is this clear? Maybe I can repeat it. So I started with some 4 hollow dots, 1 center dot. I put 2 clocks here, and then I put orientations here, and whichever path has a peak, I label this dot here. And I have 2 paths from beginning to end, which have either 1 peak or 1 dip. There are only 2 paths, 1, 3 and 2, 4. And there's exactly the 2 labels that I wanted. Yeah. You could have got 2, 4. You would have got 2, 4. Yeah. So you can generate, so it's not, I mean, I'm just saying that let's stick to this convention. It's just a convention. But right now I'm just putting clocks here. I'll do one example, it will be clear what I'm saying. So let me do n equal to 5, 5-point example. But I hope at least the message is clear that so this is called so these are called blossoms because they are like they are not they are like external, and the gentle has some technical meaning which we will not go into. No, so 2, 3 is again having no peak or no dip, so it's not we ignore it.
I mean 2 field dot. I have put only 1 field dot. I mean the center dot I have put 1. That's the field 1.
No, there is no 2. I mean this is my I'm starting like with this object. I can't put 2. Yeah. I will come to that. So right now, it's an excellent point. So it's generating both terms, but it's generating both terms in the sense that the paths are distinguished. One is a path which is like a peak, and one is a dip, and the dot has an extra data that it is preferring 1, 1, 3. Okay. So right now I have not made any connection with the basis. I will make in like few minutes. But it's right now I have only made connection with the abstract data that we had, right? So let me do one more, then it'll be clear. So let's take n equal to 5, and let's draw the sum. So now we have more choices, but I'll just draw one of these quivers. Sorry. And so then we have, let's just draw, so the number of, this is related to Arpan's question. So the number of black dots I put, that's what I was saying, the next picture will become clear, is basically n minus 3. Okay, so the number of black dots is n minus 3. So this is a, wait, we are drawing some quivers, okay, I hope it's okay. It's just, we are laying down some rules, so it's n minus 3. And now let me draw the following. So the rules are that at every black dot there should be total of 4 lines. So let's just start drawing it. So let me give you one. Oops, maybe I do it like this. Sorry. This is one example. You could draw many other examples. I just give you one example of such a quiver. And now what I want to do is, so let me put a clock here, and clock here. And so then you see that this, so if I go clockwise, I have this, and I have this. So for every, so it's exactly n minus 2. So however dots are there, you put one more clock. Okay, and you see that, so the number of clocks is n minus 2. And notice that a remarkable property of this quiver, that like here at every watt there were 2 arrows which were outgoing and 2 incoming, and it may have looked little obvious here, but that's also true here. So the way these clocks are set up, and you could change these clocks, I mean you could put one here and one here, for example, but the way they are set up, you see that now at every black dot you have 2 outgoing and 2 incoming arrows. Is that clear? And that rule you can show that is true for any n. So if you generate these blossom quivers, then they always satisfy this property. But now let's label these black dots. So you see that, so let's label this 1, 2, 3, 4, 5, and let's follow this arrow. So this is an arrow which has a peak at 1, 3. Okay, so let me write all the paths. So 1, 3. So let's write all the paths. I'm going to make a table. Peak and dip. Say the last thing again. No, it's always with one line. So if you have n hollow dots, means they are all attached to exactly one line. Oh, sorry, yeah. That line, yeah. No. So that's because, yeah, absolutely. So because I want to ensure, that's exactly. So you cannot have a line between 2 hollow dots, but you can always have a line from hollow dot to any of the black dots. Sorry, that's what you are asking. Yeah. So we cannot allow this line, but we have to construct lines which are such that number of lines at every black dot is 4. So that's how I'm building this quiver. I could have put in different places. Yeah. Yeah, so that you are right. No, one will have to be up. We have to make sure all the arrows are assigned. But there is still a choice in the clocks. And so here you see that, so let me draw now. So we have how many paths? 1, 3, 2, 4. So paths are any path that you go from, some vertex to some other vertex. So let me draw all the paths that are allowed, and I'll tell you why others are not allowed. So again, I'm not drawing 1, 2 simply because 2, 1 has no peak or dip. Similarly, 2, 3 has no peak or dip, 3, 4 has no peak or dip, 5, 4 has no peak or dip. So those ones I'm ignoring. So now let's label. So 1, 3, so let's call this dot A and let's call this dot B. So 1, 3 has a peak at A and it has no dip, so it's empty. Then if you look at 2, 4, 2, 4 has a dip at A and it has a peak at B. So it has a dip at A and a peak at B. And 1, 4 has nothing at A and a peak at B. So nothing at A and a peak at B. And 2, 5 has dip at A and nothing at B. Peak at B. Sorry. Thank you. That's important actually. And 2 phi has dip at A and nothing at B. And 3 phi has dip at B and nothing at A. Okay. 2 4. So 2 4 you go from 2. So at A there is a dip. Then you go here and you see that here they are outgoing. So there's a peak. Is that what you are asking, Ashok? Just follow the line. Yeah, exactly. No. Just no. Yeah, exactly. So I should have said that. Yeah, you should always go through the line that passes. I am not giving all definition. That's why these things are a little confusing. Because it's just some catalog of definition, but I'm doing through example. So you are right that I'm not allowed to go through any of these paths which I have ruled out. So this path I have ruled out, and that I'm not allowed to go through. We can be more systematic, but that's yeah. So that was part of the rule that when I'm tracing these paths, like I look at these paths. So this is why the name gentle comes. So basically the point is that you look at composition of all paths that form an algebra, and any path which has a length 2 and no peak and dip, you quotient it out. So which length exactly 2 and no peak or dip or anything, then you have to quotient it out. So that's it's called gentle algebra. I mean, I didn't want to go into it. No, that's not the point. 2 to 4, like this one, you can say I could have gone through this. Yes. But I cannot because I'm basically quotienting out, I'm allowing, not allowing these paths. No. I mean, it effectively could become like that for some examples, but right now I'm keeping the rules to be simple.
It's quite confusing. If you give some definition, it will help.
Yeah, okay.
So what is the precise definition?
Yeah, the precise definition I didn't want to give, but okay, I can. So the precise definition is really that you so consider all paths and so you can and look at the algebra of all paths. Yeah, you multiply and you can as a vector space add it exactly. No, just formal sum you can make. That's the algebra. Path 2, that's a formal sum. And multiplication is composition. And composition is only when you, so composition is if I take this path, then of course I can only multiply it with this path. That's the composition. So this one is a basis. Like if I go from 2 to B, it's not composed of this path and this path, it's composed of the inverse of this path and this path. So it's an algebra. So I also have a negative element which is reversing the orientation.
What is the multiplication?
It's just a source of something and boundary of something we have to do. 1 to 2 is okay. So it is.
No, I don't want to multiply it to 5 to 6.
You are going from 1 to 2?
That's path 1.
Yeah, that's path 1.
I want to multiply it with 4 to 5.
4 to 5. No, you cannot, because that's what I was about to say, that you can only multiply two paths whose source, beginning point and end point coincide.
But in algebra, you should be able to multiply all elements.
No. So you generate, this is a generating set I'm saying, then you can only add it. So you can formally add things, right? It's like a polynomial sum. So you can add some multiplication here and you can sum it. But you're not allowed to multiply two paths you cannot compose.
But this is not an algebra.
Yeah. So it's path algebra. It's some. I'm giving you a generating set of this thing. That's it. And then the point is that in this generating set you quotient by paths of length 2 which don't have a peak or dip. With no peak or dip. Yeah. No, it's fine. Yeah.
It's not an algebra because, at least the way I understand algebra,
I think it should be. I'm not able to recall the correct definition. Let me check. And there is an algebra here that I'm not.
Maybe I just add the paths, like if they're disjoint, I just add them.
Yeah, the sum is always for disjoint path. That is true. And composition is only for paths which are such that the beginning point and the end point match. No, there's a usual composition. Well, I mean, so the point is that take this element, take this path. It's a string, right? So you take the string 2a. This I can compose with AB by basically saying, I can invert AB, so it will become BA. So 2a b. I mean, if this is my AB is a path, then AB inverse is the path where this arrow is reversed. So 2a, AB inverse, B5, B6 inverse. So that's the composition, that's the multiplication. And somehow from this you generate all the elements. I mean, this is a low level definition. I think this.
You have to be able to multiply any two elements of that.
Yeah. So, other product, clearly you are right. Yeah, you declare as 0. Yeah, absolutely, you are right, because multiplication is always composition and inverse. So you are right that other products are 0. Because you are right that I could always, if I wanted to multiply some path and some other path, I could perhaps go through this path which has no peak or dip, and that I'm quotienting out. That's my ideal of length 2. So I can probably always add that. Yeah, I should be more careful, but I'm right now just doing it very sketchy. No, but that's a part of the algebra. That's the part of the structure. Yeah. So maybe can I go on? So then with this catalog.
Sorry, yeah, you should go on.
Yeah.
So AB inverse, as you said, maybe the path from 2 to wherever.
Yeah.
AB inverse. But if you look at AB, you want to say that's 0. But AB inverse is not 0. It sounds very.
Say the last line again. Say the last thing again.
You define a notion of an inverse also, right?
Yeah, of course. We reverse the orientation.
Right, but B inverse B is
B inverse. B is a point. Sorry, it's a path of length 0.
No. When you define B inverse, what did that mean?
No. AB inverse.
AB inverse. Yeah, sorry. So
yeah.
AB inverse.
Yeah.
So AB into AB inverse is 1, right?
Exactly.
Good. But now let's take that path that goes from 2 to 5. So
Yeah.
take the first arrow.
Yeah.
And multiply it with the second arrow. You said you'll have to multiply it with AB inverse, right?
Exactly. That's allowed. Yeah.
Okay. But if you multiply it with AB according to Ashok's rule, that'll give you 0 because they are not compatible. So that path, whatever you want to call it, from 2 to A.
Yeah.
Into AB is 0, but 2 to A into AB inverse is not 0, is a longer path.
Yeah. So I'm saying that, I'm generating my algebra by sequence of, these are my generating elements, and I'm giving you words, like I'm giving letters, which are each of these paths, and now I'm generating sentences.
I don't think that makes sense, right? Because
Why?
let's say I multiply 0 with AB inverse on the right hand side. I should
0
get
with
back
AB
2A.
inverse. Yeah.
Which the equation you're telling me is 2A into AB is equal to 0.
So like if you go like this,
No, I just want to go from 2.
Yeah, 2, okay.
So 2 into A, 2A, that's one path.
That's one path.
Into AB, that's 0. Because I can't join them. 2A into AB inverse is not 0, but 2A into AB, I thought you said is 0, no?
Yeah, no, 2A to AB is not, 2A to AB is not 0. I'm just giving you generators from 2A. I'm giving you letters like A, B, C. And then I'm telling you what alphabets symbols I can compose and generate words. And then I take linear combination of the words. So that's my vector space. So I take all my words, like each length is a letter. Okay, let's call alpha, beta, etc. Okay, then I will generate from it all words these are alphabets. So I can generate alpha, beta inverse, gamma, whatever.
But I can't generate alpha.
No, I cannot. So this is I'm generating something from this set of alphabets. Okay, then I can take sum, and wherever I take a path of length 2, so this is my this is the vector space that I'm starting with, and in this, whenever I see a path of length 2 which has no peak or dip, I quotient it. It is like your reduced word, right? So you have some alpha, beta. So let's look at this, right? You have some alpha, let's call it alpha prime, beta prime, and gamma.
There's no multiplication rule in this.
There is some structure, but I'm not remembering. But right now, what I have in mind is only this. I only need this structure.
Okay, so you take this set. So I think maybe we should just think of it as a set of words which is generated by combining all these things. And in this set of words, you're going to quotient out some set of words.
There is an algebra, but I'm not able to recall the definition because what one has to do is put some. Let me not say more. I just need this data that I explained to you.
Quotient out means you'll set those words to 0. You'll throw away those.
It's ideal actually. You can show that it's an ideal in the sense that all parts of length 2 which don't have a peak or dip, you can quotient it out. As at the level of this alphabet, like you reduce it basically. So that wherever you see that, you shrink it to 0, like you annihilate that word. So, okay, so with that. No, because it has no peak or dip. So every path which has no peak or dip, I am not going to list. No, I don't list. Yeah. So, so now. You just combine. Yeah. So these are So these are called improper paths. All the paths which have no peak or dip, improper walks. No. So I'm just not counting these walks right now.
So this is a separate.
It's a separate thing. So I'm only listing the walks which are not improper in the sense they should have at least one maximum or minimum. I'm not going to list anything. I mean, if I go to n, it can be more arbitrary paths with no peak or dip. They are not length 2, of course, but I just don't list them. No. The quotienting is, there are two different structures. The quotienting is by ideals of exactly length 2. These are improper walks. They are not in the ideal. They are just something I'm not considering right now. And you'll see why. So, yeah. Okay, but you see that there are only two paths which have exactly one peak and nothing else. So that's 1, 3, which has a peak at A. So this dot is 1, 3. And this one is, if you look at 1, 4, it has a peak at B and it has no dip. So this is 1, 4. And so you see that now we have the following structure. Maybe I'll write it here. No, I'm not joining anything. This dot is labeling as 1, 3 because it is because the path 1, 3 is the only path which has only peak at that vertex and nothing else. And similarly, 1, 4 is the unique path which has a peak here and nothing else anywhere else. No, 2, 4 is a dip. So 2, 4 has a peak at B and a dip at A. Yeah. But there's only one path which has only one peak at one vertex. 2, 5 has a should have a dip. Sorry, should have a dip. I wrote it wrong. I apologize. It should be dip. It should be here. 2, 5 has a dip here and nothing here. So I just wrote it wrong. Yeah, it's a dip at A. Yeah. So let me redraw. Sorry, I made a mess. So the black dots are labeled as 1, 3 and 1, 4. And we have all these 5 paths. And these 5 paths are all the paths are those which are not improper in the sense they have at least one peak or dip. So I have not written any path which has no peak or dip. And we can now look at a slightly interesting substructure, which is this one. So let's consider this. This is a full quiver, but let's consider this quiver, which is only centered around A. So if you only focus on A, and you see which are the paths which have either a peak or a dip at A and nothing else, then there are only 2 paths. So at A, which is 1, 3 dot, there is only one path 1, 3, which is peak, and there is a path 2, 5, which is a dip. Every other path has either a peak or a dip also at 1, 4. Is this clear what I've written? So if I focus on a subset of the vertices, these black vertices, and I ask the same question, like which are the paths which have peak or dip, then I get only 2 paths, which is 1, 3 and 2, 5. No, because 2, 4 also has a dip at B, peak at B. The only 2 paths which are only touching A in a non-trivial way and not touching B are 1, 3 and 2, 5. Right? The other ones also require B for their description. They are not enough to.
What is that P and D are written 1, 3 and 2, 5? What is P and D?
Yeah, exactly. So the path 1, 3 has a peak and 2, 5 has a dip. Yeah. Okay, and now this gives us 2 structures. One is a combinatorial structure and one is a geometric structure. So let me first tell you this. Just this quiver gives us two structures. Oh, maybe I do it here. Yeah. That's a definition that I'm going to label the dot with that path which has only peak at that vertex and nowhere else, nothing else, anywhere else. So there's a unique path which has a peak here, and there's a unique path which has a peak here, and no dip anywhere else. So
What tells you that all of your clocks should be
no. So you have to put the clocks in such a way that you can consistently assign arrows, but there is no unique setting of clocks. You could adjust them in different way. They are assigned in such. So you need, if you have n hollow vertices, you need n minus 2 clocks, and you have to ensure that they will give you consistent assignment of the orientation.
So that tells you that all of them should be either clockwise or
No. So clockwise and is our choice. If you choose anti-clockwise for one clock, choose anti-clockwise for all clocks. So that don't change anything. But where you put clock, there's ambiguity. But once you say that my clock is running clockwise, because we have no horizon, it will be clockwise only in all the. The time orientation doesn't change for us. So you are asking why can't I take this clock to be anti-clock? No. That's a definition, part of the definition. You could choose all of them to be anti-clockwise. That's it. It should be same. That's it. Yeah. That's an excellent question. It will, but we will see that in maybe in the lecture 2, and they give rise to geometries which give us one loop integrands or higher loop integrands. So certainly I'm giving you right now the simplest ones which do not have that subtlety, but maybe towards the end of today, if I have time, I will show you at least one example of that type of quiver. Yeah, absolutely. Many, in fact, this is one choice of combinatorial structure. If you have time, we can discuss many more which we don't even know right now if they have physical interpretation, amplitude interpretation. But I'm telling you one where we have found interesting connection to amplitude. So
why did you start with this quiver? What is special about this?
Well, that's a bit of a long history. So,
Playing a special role, right?
So say that again.
3 is playing a special role.
3.
That number, number. How many
No. That's an example. So no. This is one example where I have 5 hollow dots. I could have drawn something else.
So all of those you have to.
No, I don't. They all give same physics. Yeah. So I will comment on that. So you are absolutely correct that if I just fix 5 dots, hollow dots, 2 black dots, and I want to have 4 arrows at every black dot, 2 incoming, 2 outgoing. This is of course not a unique choice, but so there are many choices. I'm giving one example. No. Black dots, by themselves will have no connection with Feynman diagrams. They will generate some geometric structure which will give us amplitudes. Of course, you could notice that all of these have something to do with propagators because they are labeling bases. That is why we looked at this structure in the first place, because the only thing that survived, if I forgot physics, was the n and the indices of my x. So now I'm telling you some structure which picks out exactly that data, like the indices, like exactly these things, right?
Like generating that basis.
Yeah, just the index of the basis. So for n equal to 5, the kinematic space you can check is because it's n into n minus 3 by 2 dimensional, so it's 5 dimensional, and the basis we have is precisely x13, x24, x25, x35, and x14. So and the proper walks are precisely labeling those bases. So there are. Yeah, so that was the objective. That is, quivers somehow carry representation of exactly the basis that we have started with. Nothing more, nothing less right now. The ambiguity is what Ashok is asking, that we have got more, which is that we have labeled this with 1,3, this with 1,4. But I could have tried with some other quiver where this was not the one that was touching 2, one was touching like 2 of those guys. Then these black dots will be labeled by some other index. But we can draw all of them, but amplitude, we will see that we get same physics from any of them. So that choice is not important in the end. But let me now, so there are 2 structures that we get out of these quivers. One is combinatorial and one is geometric. Yeah.
Had I reassigned the clock, is it clear that whenever you have a loop like A, B, C,
Yeah.
that loop will have a consistent flow?
Yeah. If you do clear definition changing, which absolutely. You absolutely just true that the easiest way to see this is that join the join the hollow dots with some dotted. Let me look like this. So then it will be clear. So you do it. Okay, just think of this pentagon. And now let me draw this pentagon again here on the side with what we have there. So the pentagon that is there, I'm drawing it slightly differently, like this. So and you see that what I have drawn, that quiver I have drawn is precisely this. And the whole point is that there are 3 triangles. I put clock in these 3 triangles. So all the 3 cells I have, I put clocks in them, and either all of them clockwise, all of them counterclockwise. So if you draw the external lines clearly, then you immediately see how to put the clocks. So to answer Ashok's question, to other quiver would be this one. If I made some different choice, for example, this could be one choice. And so you see, this will be a different choice. Ashok, this is what you're asking, right? They are different quivers, but they will give same physics, as we will see. So that's why I didn't. Okay, but let's see what the geometric and combinatorial structure they give, which is that the fact that there are, if you look at 1, 3 and 1, 4, 1, 3 has peak at A, and 1, 4 also has a peak at A. And there is no other path which has a peak at A. So let me write it. So there are only 2 paths. There are 2 chords which have peak at A. 2 paths. Thank you. 2 walks. In other words, if I draw them with the peak and dip description we gave, then you see that 1, 3 is this one, and 1, 4 is 1, 4 is yeah. 1, 4 is this one. Yes. So it has a peak at B, no?
Yeah, but it does not have the other one.
Yeah, it doesn't have anything. Sorry, what did I say? Sorry, I said it wrong. It has no peak. No, thank you. There are 2. Sorry, thank you. Yeah.
Then it's an improper path, right?
No, it has one. It has a peak at B, na? It has a peak at B. It's proper walk. Yeah. But sorry, thank you. I said something wrong. So there are 2 walks, 1, 3, 1, 4. I'll rephrase it, which do not collide. In the sense that wherever there is a peak for one path, the other one does not have a dip. When there is a peak, wherever there is a peak or a dip at one path or at one, let's say 1, 3. Let me be more abstract. So let's say that we call any 2 walks, W1, W2 non-colliding. In the math literature, they are called non-kissing, but I don't want to use that in the seminar, so we just call them non-colliding. So they are non-colliding if wherever there is a peak or a dip at W1, there is no peak or dip at that vertex for W2. So you see that the walk 1,3 has a peak at A, and the walk 1,4 is it has only a peak at right. So you see that this is 1,3 walk and this is 1,4 walk. You can carefully see, right, because it only has a peak at B, it has no orientation change at A. So these two walks are called not colliding walks, and you can easily convince yourself that the set of all non-colliding walks is the following: 1,314, 1,335, 1,424, 2,535, and 2,425. So this is just some, I assure you, you can check it carefully that this satisfies our criteria for non-colliding walks. And for a W1, if there is a peak at some vertex, W2 should not have a, if W1 has a peak at some vertex A, W2 should not have a dip at that vertex.
Oh, it's not neither a peak nor a dip. It should not have a dip.
Yeah, if it is O, so it should be DP. Thank you, DP. So if there is a P for the one guy, there should be no D at the other, or vice versa. Okay. And so then but now this set of all non-colliding walks generate a combinatorial structure called the Associahedron, which is simply the following. No, 1,5 is not, there is no turn, so it's non-colliding with everything, yes. Yes, so but it's improper. So if you just wanted non-colliding, 1,5 is certainly there. But if you want I'm not writing all the, Ashok is giving me hard time, but non-colliding proper, I should have written, non-colliding proper. Yes. And so you see that that structure is simply 1,314. I'm just labeling an abstract. So this the set of all non-colliding walks nicely generates for us a combinatorial structure, which is this one. Okay, so every vertex of this, so this is called a two-dimensional Associahedron.
Earlier also.
Yeah.
Just to complete the definition, at least now I'm getting some sense of what is happening.
Yeah.
Can you just say for the general 1 to n thing, what is the rule for how the arrows have to be oriented?
Yes. So let's take any n gon. So let's take a 6 gon. Let me draw it in a one way, and then I'm going to draw. I'm just drawing what you're asking. So. So on every of these pink guys, I'm putting a hollow. So I'm just labeling the pink hollow thing with the pink edge just to draw it properly. Otherwise in board I get confused. And now in every cell, I just put one orientation once and for all, either clockwise or counterclockwise. So I'm just putting clockwise. And now I can remove all my unnecessary garbage, which is. Say that again? Yeah, I may have forgotten something, but just to tell what Suvrat is saying. Now I just remove these things which are not there. No. The quivers are all different. Yeah, you put. You talking about orientation. So if you put all clockwise, that's the rule. You put everything either clockwise or counterclockwise. Oh, I am not allowed to put some clockwise. No, that you are not allowed to put. That is not allowed. But you see that that's what I draw earlier. So you see that this particular quiver I'm drawing now corresponds to like a specific division of 6 gon into 3 cells. If I choose some other division, corresponding quiver is different. So there are many quivers, as many as there are triangulations of an n-gon, that many quivers are there, but they all give same physics. That's why I'm just, that I will explain. So all of these quiver don't give us different amplitudes, as we will see. You understand? So for every triangle, there's a quiver. Triangulation of any n-gon, there's a quiver. For each triangulation. So the number of triangulations are this Catalan number. So we have that many number of such quivers for n. And in every such quiver, orientation is fixed once and for all, either clockwise or counterclockwise for every cell. So that's not going to change. But there are still Catalan number worth of such gentle blossom quivers. But they all give the same physics for us, as we will see. So that's why I'm just drawing one structure. Yeah, I should not connect hollow dots with each other. That was my definition of the quiver. Yeah, I have to connect hollow dots only with the black dots, not with each other, and such that at every black dot I have exactly 2 outgoing and 2 incoming arrows. So every black dot is 4 valent. Every hollow dot can be 1 or 2 valent, and that's my rule. So that's my quiver. I think there will not be more than 2 valent, as I can see. Yeah. I think I think there are mathematicians in the audience who can maybe say more. I must say that some of this came after discovery of relevance of Associahedron in physics that I was about to, in the end I'll give reference, but the structures we discovered was by Nima and Song and their collaborators, which was a particular way to draw Associahedron in kinematic space. So these structures are the Associahedron itself is very old. It's from 60s, I think, as a combinatorial structure. But what Nima and all realized, I'm slightly going ahead because you're asking, they saw that a particular way of drawing this in kinematic space gives us amplitude of some scalar theory. Okay. But now, what gave that drawing? So they had some physics intuition, but then mathematicians realized that that's the most natural drawing you can get for Associahedron coming from purely combinatorial data of these quivers.
I see, but just before that, like, what is the motivation? You don't have to answer this, but what is the motivation to study these quivers? Like, it seems, why is it a natural structure?
Yeah, so so again, my answer is probably going to be very crazy. So one reason that I'm going to the quiver as opposed to going to Associahedron is that it's going to generate a lot more combinatorial geometries than, as I will explain in a second, than Associahedron. So the Associahedron is something where it's some combinatorial structure where every vertex is labeled by triangulation of a n-gon. So in this case, this is the n equal to 5 Associahedron. So you are triangulating a 5 gon. There are 5 ways to triangulate. Okay, but you can ask, what about quadrangulating n-gon or breaking in differential? Do they also generate combinatorial structures? As we will see in a minute, these quivers directly produce all those for us together. Yeah, so they generate a large class of combinatorial geometries. Maybe that's one reason. Maybe mathematicians can say more precise things, but yeah. So maybe gentle algebra, maybe we can ask her to explain more precisely, but yeah. Yeah, that I wanted to construct. I was being sketchy, but there's a rigorous definition that, yeah. Say the last line again. Yeah, I was about to explain that. So you start with one pair of compatible walks, okay, and now you say that, okay, what can I do such that I change this configuration, but I still end up with compatible walks. So only thing you can do is either you go, instead of 1, 4, you choose 3, 5 because these two are compatible, or you change 1, 3 to 2, 4 because these two are also compatible. And then you connect what we just wrote here. More naive, simple-minded way is that look at all triangulation. So take a structure like this. Now I'm going to call this bar because I don't want to mix different, The hollow dots that I was calling 1 was what I was drawing here. So I'm calling this a bar for that reason. So this is one triangulation. Now you say, okay, what are the triangulation I can obtain from here? By precisely changing exactly one chord. So there are only two, like you change this or you change this. So which is this one and this one. So that this is called mutation. So you go from one vertex to the other by exactly flipping one chord in your triangulation or exactly flipping one entry in your compatible box. Is that what you're asking?
But going from 1314 to 1424,
Yeah.
you flipped 2, right?
No. So I keep 1,3 intact and 1,4 got, then only I can either change one. Yeah, the walks, I'm talking about the walks, right? These are my pair of compatible walks. And they are arranged in this specific way for a reason. Any two walks which are adjacent to each other, they have one common entry. Okay, so, but now we immediately get more interesting structures, because if I look at, sorry, maybe I deleted it. Yeah, here. So if I look at this yeah.
I'm missing something, but why is 1425 not a non-collidic?
Say the last line again. 1425. Yeah. 1425. 14 and 25. 25 is 1425 is non-colliding. You are correct. 1425 is indeed non-colliding. 14 is a dip at B and peak at A. Yeah. So just give me a second. Yeah.
How this 14 doesn't have a peak or a dip at that key point?
Yeah.
It's both are ingoing and dip means that both are outgoing. But that's not happening. One is ingoing, one is outgoing. Why is 14 a proper path?
No, 14 is of course proper, because 14 has a peak at one of the vertices. No, that's fine. Okay. Only paths which are not proper are which have no maxima or minima, like what Ashok said, right? 15. So Omkar, maybe I come back to it, but okay, one way to see the compatibility is that 1425 chords intersect, in a triangulation. If I draw a triangulation, 14 and 25 chords intersect. No, I will use that, but let me, yeah, I want to use that definition, but I think there may be some structure. Do you remember what yeah, maybe let me come back, Omkar, with this. I mean, that you are right. I mean, there is something that I am not saying correctly, but okay. One way to see it is just all the chords which don't collide is what we want to call compatible box. Yeah, but sorry, what I wanted to say was that if you look at this A quiver, which has, so there was, I wrote a other quiver, which was a sub quiver in some sense, which is this one. And this has only two walks, so there is nothing compatible. There is only 13 and 25. And this structure is interesting in its own right, because it's telling us that if I start with a 5 gon, so let me draw it here. Then I have, it is only generating for me two walks. One is this one, and the other is this one. And so this structure you see is the following. I have a walk 1, 3, and I'm flipping it to get another walk which is 2, 5. And this is a one-dimensional combinatorial object. And this object is what is called a Accordiohedron. So it's an object which breaks combinatorially, is generated by breaking a 5 gon into a triangle and a quadrilateral. And it only has two vertices labeled by 13 and 25, which is directly generated from this quiver. Is that okay? Is it clear? Sorry. No. This is a abstract structure. Sorry about that. So this is the obtained by triangulating this. I'm just drawing pentagon only one way, because that's the only thing I know how to draw. But each entry is this. Each entry is this, like this. So associahedron is something where each vertex, it's a pentagon by coincidence in 2 dimensions. So the dimension of the polytope is same as the number of chords you require to triangulate, or number of independent compatible walks. Maybe that's why it's misleading. So if you had n equal to 6, you would still draw things here, but the corresponding associahedron is 3-dimensional, not 2-dimensional. But now we see that we get more combinatorial geometries, which is, for example, for each sub-quiver, we got a 2-dimensional associahedron on one side and a 1-dimensional accordiahedron on the other side. And this is a structure which breaks my pentagon into a triangle and a quadrilateral. So the statement is now that if you give me, now we can flip this around. So again, so this is the first part of the stuff that our quivers give us a large class of combinatorial geometries. The first one is, so fix n. And the first geometry we obtain, class of geometry, is called associahedron, which is n minus 3-dimensional. No, 1, 4, 2, 5 collide. I think my definition, I'm not saying something correctly, but 1, 4, 2, 5 are not included because if you dissect things here, 1, 4, 2, 5 are not triangulating anything.
No, here in this row, you wrote 1 bar, 3 bar, and 2 bar. Yeah.
Yes.
1 bar, 2 bar.
Yes, that's the flip. Yes, that's the flip. So I am saying that our quiver, so this is my sub quiver, which is, if I focused only on 1, 3 as a vertex, then there are only two walks which have either a peak or a dip only at 1, 3 and nowhere else. Because if you look at any other walk, it has either a peak at B or a dip at B. Only walks which are insensitive to B are 2 walks, which is 1, 3, 2, 5. So, and one has a peak at 1, 3 and one has a dip at 1, 3. And that generates a 1-dimensional combinatorial structure. And that structure is same as if you take a pentagon and you say, well, I'm dividing it into a triangle and a quadrilateral with 1, 3. What can I generate? This is telling me that I'm only allowed to do one flip, and that flip is 2, 5. I'm not allowed to do any other flip. I'm not allowed to do it by that structure. So it generates for me specific combinatorial geometry. It's just, I'm just reading from that structure. Yeah, exactly. So the n minus 3-dimensional geometry is associahedron, which is same as, schematically obtained by set of all triangulations of an n-gon. Absolutely. Associahedron would be insensitive to the whichever thing you start. No. You get different accordiahedra, because if you start with B, excellent. So if you start with B, then you see that at B you have a peak for 2, 4 and a dip for 3, 5. So you get an accordiahedra which is 2, 4 and 3, 5. So you get different, you get 2 accordiahedras. I will write that here. So you get, sorry, where did my, yeah, here. And then you get, so you get AM for M less than N, accordiahedra, which are generated by set of all dissections. I'm writing it again a bit schematically because you could choose any dissection that you start with. So let me explain this a little bit in more detail now, what this structure is. So just to repeat what I said now. So start with any dissection. So let me give an example. So let's say you start with a 6-gon. This is equivalent to what we did so far from the quiver, but it's an easier way to probably understand it. And let's say that you start with this dissection. So it breaks your 6-gon into 2 quadrilaterals. And now what you do is look at all the edges which is adjacent to this chord. So only 4 edges. These 2 edges are not touching this chord, and so put hollow dots on them. Okay. And actually let me call this 1 bar, 2 bar, 5 bar, 6 bar, and let's call this 1. This is 3. This is coming to the right of 1, so I'm calling it 1. This is 3, this is 4, and this is 6. And now you see that there are only 2 allowed chords, so there is this chord and there is this chord, which also 1, 4 is already same as 1 bar, 4 bar. So that breaks the 6 gon into 2 quadrilaterals. But 3, 6 also breaks it into 2 quadrilaterals. So you notice that we obtained one-dimensional accordiahedra. So this is one example of an accordiahedra which is obtained by dissecting a 6 gon into quadrilaterals. And this accordiahedra depends on what you start with. So because you start with 1, 4, you are only allowed to flip to 3, 6. And you get a one-dimensional accordiahedra. But I could have started with breaking an n-gon into some half triangles, half quadrilaterals, whatever I wanted. And I would always obtain some combinatorial structure. And that structure actually would all arise from a single quiver. So take a quiver with n and take some sub-quiver and look at all possible such combinatorial structures. So this is one full class of geometries that, okay, when do you have to stop you tell? Oh, we are done. Okay. This is full one class of combinatorial structure that we obtain. So maybe I can continue from here, but if you have any questions, please ask.
All the different triangles and quadrilaterals, you will have different.
Yeah. So if you look at triangulation is unique because there is no choice. I mean, set of all triangulations is such that if you start with one triangulation, you scan, you get all triangulations. But as we are seeing here, that quadrangulation is not unique in the sense our rules from Quiver is telling us that if I have with 1, 4, I can only flip it to 3, 6. I cannot go to 2, 5. But that's the rule that came from the Quivers. So so it depends on the starting point. 1, 4 gives me one-dimensional accordiahedra. 2, 5 will give me other two accordiahedra, etc. So Associahedron is unique in that sense, that it doesn't matter what we start with, we always get the same combinatorial structure.
For higher point, like
There are all these geometries, and what I will do next time is to show that all the accordiahedras are in a specific sense just some projections of Associahedra. And so Associahedra is like a master geometry that we work with. Everything else just comes from, and that is clear from here because it's all coming from the subset of the vertices that we started with, right? Is this? I hope this is clear. So by looking at both the dots, we got Associahedra. By looking at one of them, I got some other geometry. So clearly Associahedra is like generating set for everything else. Yes.
So you generated one accordiahedra using just the paths that have
Yes.
But I could do three.
Exactly same with B, and that will give you accordiahedra which is 2, 4, 3, 5. So if you start with B, then the corresponding accordiahedra is 2, 4 and 3, 5. So that's also one-dimensional combinatorial geometry, which is basically just this. And you can ask what it means in terms of dissection. It simply means that you start with some pentagon. And you start with 2, 4. And you are only allowed to flip it to 3, 5. So this vertex corresponds to this dissection into a triangle and a quadrilateral, and this vertex corresponds to this dissection into a triangle and a quadrilateral. But you could, if you go to n equal to 6, where you have like 3 dots, then you could start with 1 dot, you get one-dimensional accordiahedron. If you have with 2 dots, you get two-dimensional accordiahedron. So with for every n, you need to put n minus 3 black dots. And then you get a whole bunch of, you get one Associahedra, which is all the walks, but you get a whole bunch of accordiahedra, which depends on whether you take 1 black dot or 2 or 3 or whatever. So you start generating an entire family of geometries. And remarkably, all of them are tied to amplitudes in scalar field theories that we will see next time.
You mentioned that Associahedron is a much bigger geometric object.
Yeah, it's the highest dimensional.
But is it correct to say that from here we see that your accordiahedra is dissecting it into a triangle and a quadrilateral?
Yes.
Associahedron dissects everything into triangle.
Exactly.
So it's a much bigger set as compared to.
Exactly, that's the point. So every other because the dimension will depend on how many black dots we are looking at. But every Akkadiahedra is lower dimensional than Associahedra. So Associahedra is always n minus 3 dimensional. That's it's simply the number of chords we need to triangulate, and then depends on how many, as you said, dissections we are doing. We get Akkadiahedra of varying dimensions. But the remarkable fact is that we will see that once we draw them geometrically, all of them are like shadows of Associahedra. And this basically tells us how, as you will see, that every such Akkadiahedra gives us tree-level amplitude for some phi to the p theory, and all those amplitudes can be obtained by some specific geometric projections of phi cube theory. So it's really going to be like one universal object whose drawing is going to generate for us like an entire class of amplitudes of quantum field theories. So that's the, yeah. Yeah.
So, combinatorially, I understand that this is the same as the ABH.
Yeah.
But the ABHY also.
Yeah, that was my second part, precisely, but we want to draw it. And the remarkable, so maybe I can take 2 minutes, Suvrat? Yeah, the amazing thing is that this is what inspired these mathematicians to look at this, that the statement is that now, I'll just take 2 minutes, because yeah, this is one of the main points I wanted to actually cover. Sorry, I ran out of time. So, what we can do is, so we have, for example, here we have two, let me call it, so we have A equal to 1, 3 and B equal to 2, 1, 4. And let me assign for every walk one vector. So you see that 1, 3 has a peak at, so A is same as what I was calling 1, 3 dot. Okay, so 1, 3 has a peak at A, nothing at nothing else. So I'm going to say that the 1, 3 walk has a vector which is aligned, which has a +1 entry along unit. So with A I'm associating a unit vector, let me call it I hat, and with B I'm assigning another vector, let's call it J hat, orthogonal vectors. And so you see that 1, 3 is this. Then if you look at 2, 4 is a peak at B and a dip at A. So it has a component, I'm going to assign -1 here and +1 here. And similarly, if you look at 1, 4, you can check it is 0 here and +1 here. 2, 5 is -1 here, 0 here, and 3, 5 is 0 here, -1 here. Now let's draw these vectors. So these vectors are, Suvrat, just 1 minute, I will just end. So in the two-dimensional plane of I cap, J cap, it's a completely abstract thing, where I cap is the unit vector which I have just randomly associated to this A and this to B. So I get, for every proper walk, I get a vector. So this is the vector for 1, 3. This is for 1, 4. This is for 2, 4. This is for 2, 5. And this is for 3, 5. Now I ask, can I draw a convex polytope whose normals are exactly this? And that's precisely ABHY. Yeah. So I'm saying that we have these two vertices. I'm assigning to them unit vectors, I cap and J cap. And now I'm going to say that for every walk, I'm going to get a particular vector. The assignment is wherever there's a peak, I put +1. If dip -1 and nothing, 0. So then I get, for every such walk, I have a vector. These are called G vectors. And they vectors span this two-dimensional space, which is this. And now the whole point is, I ask, is there a realization of my combinatorial structure that is such that its faces are normal precisely to these vectors? And that's the, as Shruti was asking, that's the Associahedra that physicists found directly first by some other arguments. So, but now the remarkable thing is that we could do it for any Akkadiahedra, and we will get realizations for all possible such geometries. Yeah, but this we will do in detail maybe next time. G vectors actually did exist, not in this language. It did not exist before ABHY. Yeah, I should give some reference actually. So let me just at least give reference. Sorry about, yeah. So, so there are a few papers. So one is a paper by So in some sense, ABHY is the, as Shruti was saying, the first paper which kind of got this from physics argument. But their arguments, yeah, so this was formalized more by U. Thomas and their collaborators. Actually, sorry, I am forgetting another author here. This was in 2018. And then the everything I said, where they generalize this to any Akkadiahedra is and this was in 2019. So they kind of did everything for these general algebras. They showed how the structure of G vectors can be obtained for any Akkadiahedra and how ABHY can be generalized. In general, G vectors, of course, were understood combinatorially by Pilod and Manville even before, but not connected to ABHY. And geometric description, everything together.
Yeah, everything together, but individually, if I focus on one of them, the geometric description existed.
No, the geometric description that gave us physics did not exist before. Associahedra, there were many other convex realizations that people, of course, had found, but not the, as far as I know, I may be wrong, that ABHY had. It was formalized in also after ABHY paper in terms of.
What I mean is, after ABHY, Akkadiahedra, which you can
Yeah.
formulate without the quivers, right? I mean, separately as quadrangulations of the.
Yeah, but the issue is that for there was no before this paper, there was no unified description of why all these different realizations come from some same underlying structure. Like that was, as far as I know, that was certainly not available for Akkadiahedra is anyway a bit new. I think they are relatively new, maybe in math literature also 10 years or so. It's not that, unlike Associahedra, which is 60s. Yeah, sorry, I went over time. Yeah.
I'll suggest we postpone further questions to coffee, and we thank the speaker again. Thank you.
Thank you.